My name is Lynette Chia, and here's a short video describing a white paper that was submitted for the Global Young Scientist Summit, the topic being how to create an adaptive urban transportation system. Now, urban population has been growing dramatically, and the corresponding rise in travel demand has presented a lot of environmental and health challenges. Half of the world's population already live in cities which suffer traffic congestion, air pollution, noise pollution. So the challenge is how can we create or evolve the current transportation system into one that is more sustainable while ensuring that its users continue to get access to the services and goods that they need and continue to get the mobility that they require. So the opportunity presents itself in different forms of technologies that are becoming available to sort of manage and control or plan for the dynamics and the demand and supply components within the transportation system. So we refer to these as parallel computing technologies, sensing technologies, mobile computing technologies, as well as large databases that are making it possible for us to understand and monitor the supply and demand of travel.
In our vision, the entire transportation system is an integrated whole with the supply and demand, where we have the private transport supply infrastructure, the public transport system, the taxi system, the air and sea hubs, and any other transport supply service such as car sharing, bike sharing, BRT, or even the pedestrian infrastructure. This system provides mobility for citizens that have different requirements and profiles. The massive amount of data generated enables the awareness of the supply in real time. This in turn translates into decision-making information for the supply management itself, but eventually turning into services for the demand. With active intervention, commuters shift modes in response to system disruptions. Taxis would converge at places with predicted high demand. Shuttle buses with dynamic or reconfigurable routes ply the city's streets. Taxi and car commuters share rides and vehicle occupancy rates reach near capacity. Bus and train frequencies are automatically adjusted. Flexible traffic signals adjust their timing according to traffic counts to efficiently smoothen traffic flow. In order to create an adaptive transportation system, several enablers must be in place. Accurate real-time information on the state of the system must be available. Information on different modes of travel must be integrated into a single, seamless system. And finally, vehicles, infrastructure, and commuters must be interconnected.
We are proposing 2 projects to develop the vision of an urban adaptive transportation system. To understand the state of the system, our first project is CloudCar, a new, standardized, secure, and cost-effective way of acquiring high-resolution vehicle data. As an open telematics platform, CloudCar consists of 2 key elements: the application programming interface and the CAN-puter. The system architecture shown describes how, after a user plugged in the CAN-puter to their vehicle's OBD2 diagnostics port, their location and many other signals describing their vehicle will be securely projected into the cloud. Authorized third-party applications can access the user's data to provide value. CloudCar lets us maintain accurate real-time databases for the locations and estimated arrival times of all vehicles in the system, thereby allowing public fleets such as taxis and buses to optimally interface with each other. The CAN-puter is a key element of the CloudCar standard. It is a very low-cost, plug-and-forget data logger for collecting and transmitting vehicle data to our secured server. This includes GPS, accelerometer, and detailed engine data. The data collection system can be integrated into all types of vehicles, taxis, cars, and buses, etc. The system is open-sourced, allowing many different applications to coexist on the CloudCar platform while maintaining certain firewalls to ensure system security and user privacy is maintained. Our plan is to deploy these devices into 100 vehicles in Singapore to test and demonstrate CloudCar's feasibility and benefits.
The second project involves developing a personal, intelligent, multimodal travel advisor for commuters in Singapore that provides accurate and timely information in a convenient manner. Using existing data sets, the service offers the following: personalized pre-trip alerts, information during the trip, and post-trip travel performance scoreboard. Let me walk you through a user scenario now. Consider a user who commutes to work daily by driving a car. He usually departs at 8:30 a.m. in order to reach his workplace by 9 a.m. Before the trip, the mobile app is aware of the state of the network and the user's schedule and destinations. On this particular day, there is a road closure on his usual route due to an event such as the Formula One Singapore Grand Prix race. Whenever this information is made available, the commuter receives an alert of the disruption, and the advisor offers a few options. Now, he could drive, but take an alternative route departing at 8:20 a.m., or take a train departing at 8:15, or take a less crowded train departing at 8:10, or he could also take the bus departing at 8 a.m. The commuter decides to take the bus, but he misses it. According to the advisor, he should now either take an alternative bus route or take a taxi, which will cost him a fare of $15. The advisor thus alerts users of service disruptions in his planned or default mode and route, and suggests alternative departure times and modes in a timely fashion. After the trip, the commuter is able to track his performance daily and weekly in terms of total travel time, transport cost, and environmental impacts in terms of carbon emissions. The performance is also tracked on a scoreboard like a game. Gamification is used to motivate users to improve their travel performance by comparing their personal standings relative to other users. To demonstrate the benefit of decongesting trips, for example, a histogram of travel times are shown over the course of morning and evening peak travel periods. To demonstrate the benefit of eco-driving, fuel mileage is also reported for similar vehicle models like that shown here. To demonstrate the benefits of modal shifts, relative cost and carbon savings are shown. This encourages users to improve their travel choices and behavior. Singapore is an ideal location to test these demo projects and eventually revolutionize a transportation system for several reasons. Singapore is an island with constrained boundaries. It already has extremely rich travel data being collected. Its population is very technology savvy. The government is very dynamic and supportive of adopting new beneficial technologies. This work can be replicated in any major city committed to improving and upgrading its transportation system.
I hope you've enjoyed our presentation. I'd like to introduce our research team now. Again, my name is Lynette Chia from A-Star.
Hi, I'm Francisco Pereira from SMART, Future Urban Mobility. I work in real-time traffic prediction, machine learning, and ubiquitous computing.
I'm Eric Wilhelm from the SUTD. I'm working on CloudCar, an open telematics system which we think will revolutionize how we interact with our vehicles' data.
Hello, my name is Steven Zoff from MIT. I study what choices people make and how travelers behave when using flexible shared vehicle systems.
Hi, my name is Jeff McCauley, and I work at the Fraunhofer USA Center for Sustainable Energy Systems, using applied R&D to help commercialize new clean energy technology.
I'm Don McKenzie from MIT. I study how factors like cost and convenience affect traveler choices.